All right, 13, 1, 2, and 4 are looking at something you're going to spend a fair amount of time in calculus looking at, which is the concept of a limit. So we're going to start with a graphical example here. So here I have 4 functions graphed. They're all very similar, but they all have kind of slight differences. So the first thing we want to find is just f of 2. So that's easy. We've done that before. That's just saying, look at the graph. When x is 2, what is y? So it looks like that would be 4. The second one here, actually that graph is undefined at 2. So I would say f of 2 does not exist. About for number 3. So remember, I want to list the closed dot as opposed to the open. So that would be 1. Okay, rather than that guy up there, 4. Okay, same idea on number 4 here. I'd want to list the closed dot. That'd be 4. Okay, so I've gotten this part done, listing f of 2. The next question is actually evaluate this limit. So let me just write down here, kind of a basic definition or an explanation of what this is asking. So how I would read this, the limit as x approaches 2 of the function f of x, or the limit as x goes to 2 of the function f of x. And so this is saying as x gets close to 2, what, if anything, does the y get close to? That'd be a very basic interpretation or translation of that limit into a question. So that limit is saying, look at the function as the x's get close to 2. What, if anything, do the y's get close to? And so if the y's get close to some number L, we would call that number the limit of the function. Okay, so let's look at these guys. So the limit, as x approaches 2, the first function, squeeze all these in here. This one a little lower for the last one there. Okay. Okay, so let's start looking at the first graph. So as the x's are getting close to 2, here's 2, right? So we're coming along this way and this way. That's what's happening as the x's are getting close to 2. So you can see as the x's are getting close to 2 here, the y's are getting close to 4. So we would say the limit is equal to 4. Now notice for number 1, This function, it's not all that interesting because you see how the value of the limit is the same as the value of the function? Well, that actually makes sense because graph number 1 is not all that exciting. It's just a continuous curve. Okay, so the value of the limit would just be the value of the function itself because I just have a continuous function. Let me look at number 2. See if that's more interesting. So again, as x gets close to 2, we're coming in here, right? Zooming in on x is 2. So you can see the y's are still getting close to 4. So the interesting thing with this graph is even though the function itself is not defined at x equals 2, the limit actually does still exist because the limit is not concerned about what happens at the point itself, just as you get close to the point. So that limit is still equal to 4, even though the second graph is actually discontinuous at x equals 2. Okay, what about number 3? Okay, so again, getting close to x is 2. So getting close to x is 2, the y is still getting close to 4. This limit would also be 4, okay? Even though at the instant when x is equal to 2, I jump down here, that only occurs at the instant when x is equal to 2. So again, that does not actually affect the limit because the limit is concerned with what happens as we get close to that x value, not actually what happens at that value instantaneously. What about this last one? Okay, this one's kind of the more interesting one. Because when I'm looking at that guy, let's see, I kind of want to make some more room here. Well, I think I'm going to move that guy actually, so we have a little bit more room to look at number 4. Put that over here. Okay. So let's look at number 4. So we already evaluated, f of 2. Then the question is, well, what about the limit? So the thing is, as we're coming in from the left side, the values of y are getting close to looks like 4. But as we're coming in from the right side, the values are getting close to 5. So in order for this overall limit to exist, it has to be equal to a number, some number L. Okay, but because I have 2 different values coming in from one side versus the other, actually what I would say about this limit is I would actually say this limit does not exist because I have 2 different values. Okay, but I could say this. What if I say the limit as x goes to 2 and I put this little minus up here? So this is a one-sided limit. This says the limit as x goes to 2 from the left or from below. Okay, so that means look at the graph and look at what happens as x approaches 2 from the left side, so from values smaller than 2, okay? So what do the y's get close to? Well, the y's get close to 4. Versus if I say the limit as x goes to 2 from above or from the right. So this one says the limit as x goes to 2 from the right, from values bigger than 2. Okay, so this time I'm coming down this way. The values of y are getting close to 5. Okay, so what do I see? Well, I see that these are the one-sided limits. I see that these one-sided limits exist. Okay? But I could kind of write a statement like this. I could say the limit as x goes to 2 from the left, that's what, 4, is not equal to the limit as x goes to 2 from the right, that's 5. Therefore, the overall limit as x goes to 2 of the function does not exist. That's just a little bit more formal way of saying what I really said earlier, which is, well, in order for the overall limit to exist, I have to be zooming in on the same number from both sides. In other words, the one-sided limits would have to be equal in order for the overall limit to exist. Okay, so that was looking graphically. So what we're going to look at next, we're going to look at a series of functions, and we're going to talk about some different ideas for how I might be able to evaluate these limits. So something like number 1, I have a rational function. So I guess I have a couple ideas for this one. Let me start with something kind of really basic, and let me say, well, I guess one way I could evaluate a limit would be, well, if I think about the definition of a limit, let me set this up first, and I'll go back to what I was thinking. Okay, so what is this asking me? This is asking me, as x gets close to -5, what, if anything, does the y get close to for this particular function? Okay, this one. So my goal is to answer that question. So I guess kind of the most basic way I can think to answer that question would be I could actually set up a table of values. And I could say, well, what if I pick values of x that are getting close to -5, and I see what the matching y values are? Okay, so let's see, I don't know. -5.1, -5.01. Then I have to do both sides, -4.9. Actually, let's see. Let's even go closer, -4.99. Okay, let me plug this value in. So this is going to be what? -5.1 minus 1 over -5.1 squared. Okay, so this is a calculator problem. So let's see, make sure you can enter this in your calculator and get the same number I get here. Looks like -10. Okay, let me try the next one. -100. Okay, so next one. These are a little tedious, entering these in the calculators. Let me write this out. Okay, so -5.99 divided by 4.99 squared minus 4 times 4.99 minus 5. Okay, I get 100. So I mean, if I'm not sure what's happening, I could pick a value like -4.999, but I think I can tell just with this information what's happening here. So I would say, you see how these numbers here are not tapering off to a value? So I would guess if I plugged in -5.001, I get -1,000 on this side. -4.999, I get 1,000 on this side. So from the left side, looks like I'm going to -infinity. From the right side, I'm going to +infinity. Okay, so because the y values here are not approaching a specific number, but are rather shooting to infinity, I would say this limit does not exist. Okay, but I wanted to do the same thing looking at as x goes to 1. So do one more of these with a table, and then I'll kind of point out what's another idea, because using these tables is not really all that much fun. Okay, so now value's close to 1. So I don't know, 0.9, 0.99. I need some on the other side. Start with those, say. Okay, so what is this one? It's 0.9 minus 1. 0.9 squared plus 4 times 0.9 minus 5. Okay, say approximately 1.02611. Okay, let me do the next one. Okay, looks like I'm getting about 0.1669. Okay, let me try the one on the other side. So I'll write one of these out. 1.01 minus 1. Okay, get about 0.1664. Okay. Try this last one. 1.01, 1.1 minus 1. This one I get about 0.164. I'm double checking this first one. And I think this first one have a typo. This one should be 0.1695. Okay. So I mean, the thing with doing these by a table of values is, while there are a few issues, we need a calculator. It's kind of a pain to enter these things in. You see I probably missed a parentheses or something somewhere. I got that first value off. And then even once you do get all the values correct here in the table, well, then you have to kind of look and you have to say, well, what does it look like is happening as the x is getting close to 1 here? Well, this time, to me, it does look like the y values are tapering off to something. But it's kind of difficult to see. I mean, maybe like 0.167 or so. So we'll call that limit 0.167. But I kind of have to estimate. I can't be as precise as I would like to be there. Okay, it looks like that limit does exist. So then, well, what about a different way other than using a table? So a table is kind of a nice backup method. So if I have a function that I cannot manipulate algebraically, I may have to rely on a table of values to find the limit. But actually, with a rational function like this, I'm going to look at another idea. So what if instead of using a table, we find this limit algebraically? Okay, so what I'm going to do is I'm going to look at the rational function, and I'm going to say, well, can I simplify that rational function? Okay, so I think I would try factoring. So how does that factor? X plus 5 and x minus 1. Then I can cancel these. So it looks like the limit as x goes to -5 of 1 over x plus 5. Notice with my notation, so with these sections especially, the notation is really important. So you see how in each of these steps here, I haven't actually evaluated the limit yet. So that limit sign remains in front. Limit sign in front of each and every step where the variable remains. Okay, because all I'm doing so far is I'm just simplifying the expression. See how in all of these steps, the variable still remains. I haven't actually evaluated the limit yet. I'm just simplifying the expression. Okay, so then I say, okay, in the reduced fraction, can I then evaluate at the given x value? So when I plug -5 in there, I get an error. So I would conclude that that limit does not exist, which is the same thing we concluded via the table, but I've done a lot less work this time. Let's look at this next one. I'm going to do the same thing here. We got what, 0.167? So instead of using this messy table, all these decimals, I'm going to see if I can find this limit algebraically. So it's the same rational function. So that means the first thing I would do would be I would simplify that rational function. So that's what I already did above, right? So I mean, do I need to write all that out again? So limit, x goes to 1. Okay, so again, all these steps where I still have the variable, I still have the limit sign in front. Now in the reduced fraction, I go ahead and plug the value in. So notice in this step, I no longer have a limit sign because I no longer have a variable. I've actually evaluated the limit this time. Okay, so this time I can see precisely the value of the limit. It's 1/6. And so I can see precisely the limit is 1/6, which is indeed approximately that, what was it, 0.167 that we got via the table. But I don't have to estimate this time. Okay, so here's the same function. So I'm going to do this one algebraically, but this one I just wanted to point out, I mean, I could do the same thing, as in I could reduce the function, etc. But actually this time I don't have to. Because actually, can't I just plug the x value in immediately? And don't I get, let's see, -1 over -5, 1/5? So I can tell you the value of that limit immediately. That's because nothing interesting happens at x equals 0. this function is continuous at x equals 0. So actually, to find the limit, all I have to do is just evaluate at x equals 0, right? Versus, if you look back at the previous two here, these ones I had to do more investigating. Because you see how if I try to just plug the value -5 in, here's what I get. Oh, you see how I get -6/0? So that means I have to do a further investigation to determine if the limit exists, because when I get something like this, I know that something interesting happens at the value -5. Same idea with part 2 here. Like if I was to just try to plug the 1 in, well, what would I get? I'd actually get 0, but I would get 0/0. This is called indeterminate. That means I don't know what happens. Something interesting happens at x equals 1. So I have to actually plug, or I actually have to do the process then of simplifying the expression. Okay, but what I'm getting at is, well, the first thing you could always try is, well, can I just plug the value in? Because if I can just plug the value in, the function is continuous at that value, and then the limit problem becomes very easy. Okay, so then the last thing I was going to do with this function is just see, well, what the heck is going on graphically? This will be a nice little review of how you would graph a function like this. Okay, so let's see. Again, well, I could do the simplifying. So do you remember what happens when a factor cancels like that? Remember what that means? That means there's a hole at x equals 1. So that means we have to go back at the end and place that hole on the graph. But other than that, we're going to create our graph just by looking at the reduced fraction. Okay, so then what are some things I could find? The y-intercept, that'd be 1/5. Okay, what else? Maybe, well, x-intercepts, if I set that function equal to 0, to move this guy out of the way. Okay, if I set this guy equal to 0 and I clear the fraction, I get 1 is equal to 0. Not true, there are none. Okay, what are some other things that we found as far as irrational functions? We found vertical asymptotes. So for those, I look at the reduced fraction. Okay, and I look at the denominator. I say, what numbers would make the denominator 0? X is -5. Okay, there's my vertical asymptote. To Move this a little bit. Okay, be good enough. Okay, what else did we look at? We looked at horizontal asymptotes. Okay, for those, remember what I had to look at? I had to look at the leading terms. So if I'm looking, I can actually look at either the original function, look at the leading terms here, or the reduced fraction. Either way, so when I look at those, I get it's 1 over x or x over x squared. Either way, it reduces to 1 over x. So then I say, well, remember, what does a horizontal asymptote tell me? It tells me what happens on the ends of the graph. So remember, on the ends of the graph, I'm thinking about what happens as x goes to positive or negative infinity. So as x goes to positive or negative infinity, 1 over x goes to 0. So I know my horizontal asymptote is y equals 0. In fact, we said anytime the denominator has a higher power than the numerator, the horizontal asymptote is just going to be y equals 0. So that was kind of the simplest case as far as finding horizontal asymptotes goes. Okay, so should I dash in? Try to dash that horizontal asymptote in. Okay, so then I bet you I can tell you what this graph is going to look like. Remember, if you look at this, what does this graph look like? It looks like a rational function shifted left 5, right? So isn't it going to look roughly like so? Okay, what is the one thing I haven't accounted for? The whole at x equals 1. Okay, so to account for the whole, I guess I'll clean up some of this. Okay, so the whole, we have to get the corresponding y value. So we have to plug x equals 1 in the reduced fraction. Okay, so f of 1 is 1 over 1 plus 5, 1/6. So my whole is at 1 1/6. So there's that. And so there's a nice complete graph. So that's a nice little review. So I was really interested in kind of looking at, well, how does that graph match up with some of this information that we found? Like, okay, let's see here. Here we found that the limit as x goes to 0 is 1/5. So does that make sense graphically? Well, as x is getting close to 0, we're coming in here. So indeed, the y value is just 1/5. So that looks good. Let's see what else we said. We said the limit as x goes to 1 is 1/6. Okay, so as x goes to 1, okay, you see how here I have that hole in the graph, but the y values are still approaching that number 1/6 because we're not actually concerned about what happens at the instant that x is equal to 1, just as we get close. Okay, what about up here? We said the limit as x goes to -5 does not exist. Okay, well that makes sense, doesn't it? Because as x goes to -5, we're going to -infinity here, positive infinity here. Okay, so indeed that limit would not exist. So all of that makes sense, and we got a nice little review on graphing while we were at it. How about one more part to that one? What about the limit as x goes to infinity? Actually, we already kind of answered that. Look at the graph. As x goes to infinity, what does y get close to? Doesn't it get close to 0? So I can actually tell you the answer to this one immediately. The answer to this one is just 0. Okay, because how do I know? Well, I know a rational function approaches its horizontal or slanted asymptote on the ends. Okay, so that means I can tell you immediately, as soon as I look at this rational function, because it has the higher power in the denominator, I can tell you immediately the horizontal asymptote is 0. So that means that I know the limit as x goes to infinity, or I could even do this. I could even make this -infinity. Okay, because a rational function approaches its horizontal asymptote on both ends. So actually either way there, that limit would be 0. Now, I know the answer. I still need to justify that. So how am I going to do that? So let's leave that a positive infinity. So I know the answer is 0. What I'm going to do is I'm going to justify that. So what I'm going to do is I'm going to look at the rational function, and I'm going to look for the highest power of x that appears. So in this case, that would be x squared. And so what I'm going to do is I'm going to divide all terms in the rational function by that highest power of x. Okay, so notice I'm bringing that limit sign along. Haven't actually evaluated. Then I'm just reducing these fractions. Okay, now as x goes to infinity, any of these terms that still have an x in the bottom, these will all go to 0. So what will that leave me with? Leave me with a 0 in the top and a 1 in the bottom. So the result there would be 0. And so you can see there again that once I actually evaluated that limit where I no longer have the variable x in there, that's when my limit sign disappeared, when I just have a number. So that number is the value of the limit. Okay, so I justified that result. Okay, what about like a number 5? The limit as h goes to 0, square root of 16 plus h minus 4 over 8. So I mean, the first thing you could try is, well, can I just plug 0 in? Well, it's not going to work. I'm going to get a 0 in the denominator. So that means I have to try simplifying. So here's a little trick that we've used before. So what I'm going to do is I'm going to multiply by the conjugate. Remember, that means I change the middle sign. Okay, now I have to place that conjugate top and bottom. Okay, should I write out this was the conjugate? Okay, and then I do the FOIL. Okay, so I'm doing a FOIL here. Notice I still carry that limit sign. Okay, then I get plus 4 of those roots, minus 4 of those roots. Cancels, right? That's why this trick works. Bottom, I'm just going to multiply straight across. And then I should be able to cancel the h's. Okay, now I say, so in the simplified expression, can I now plug the value h equals 0 in? So notice this is the step where my limit sign disappears, because that's where I've actually evaluated the limit. I no longer have a variable there. So that limit does exist, and indeed it's equal to 1 over 8. Okay, what about something like number 6? All right, so I mean, if you try plugging in 0, you get an error. So then I think, okay, well, I'll try simplifying. So I think I would try an LCD. But I'm kind of thinking, okay, the second fraction, it's like so, right? So actually the LCD is just this x times x plus 1. Notice my limit sign is coming along. So I have to multiply this first fraction by x plus 1, right? Top and bottom. Second one already has the LCD. Okay, so what is that? Negative x minus 1 plus 1? again, my limit sign still comes along. I still have variables. Now I substitute the value in, so that's where I'm actually evaluating the limit. So the result is 1. So that limit does exist. Just take a look at what's left here. Got a few more. All right, let's look at a couple more limits at infinity. So it's important to look at the type of limit problem before doing anything, because if I'm finding the limit at a number, like here, that's really a completely different process than if I'm finding the limit at infinity. Okay, so if I'm looking for the limit at a number, what do? Well, I try simplifying the expression, be that factoring, an LCD, the conjugate, whatever is appropriate for that specific problem. If I'm finding the limit at infinity, that is completely different. So limits at infinity are the easy ones, because that I can tell you immediately. I'm just looking for the horizontal or slanted asymptote. So these guys, I know the answers immediately, and all I have to do is justify the answers. Okay, so when I'm looking at this, I go, okay, well, remember, to determine the horizontal or slanted asymptote, I'm looking at the leading terms, right? So I'm going, okay, in this case, I have the same power top and bottom. So what's going to happen is I'm actually going to cancel out, and the result is going to be -2. So I can tell you immediately the answer to this question is -2. Okay, however, I still want to justify. Okay, so how am I going to justify that answer? So remember, I divide by the highest power of x. Okay, so the highest power of x, in this case, well, it's just x to the 1. Okay, so let's see, that's going to leave me with -4, 5 over x. Okay, and then I go, any of these terms still have x in the bottom, go to 0. Okay, so indeed, I have verified the result is -2. Okay, what about number 8 here? Okay, so again, first thing I do, I notice I'm looking for a limit at infinity. That means I'll be able to tell you the answer immediately just by looking at the leading terms. Okay, looking at the horizontal asymptote. Okay, so when I look at the leading terms this time, what do I see? I see 2x squared over x cubed. So when I reduce, that's 2 over x. Okay, so what's going to happen to this as x goes to infinity? That is going to go to 0. So I can tell you immediately the answer to this one is 0. Okay, but again, going to do the justifying part. Divide all the terms by x cubed. Oh, and actually I think I can make my conclusion in this step. So all of the terms with the x in the bottom are going to go to 0. So indeed, as we knew, that limit is going to be 0. Okay, number 9. Okay, limit at infinity. I should be able to tell you the answer. When I look at the leading terms, well, this time I see 2x to the 4th over x cubed. So this time I'm left with 2x. So this is actually not a horizontal asymptote. This is a slanted asymptote. So actually, even without doing any further work, can't I tell you, I mean, my asymptote looks like this. Isn't the function going to go to infinity as x goes to infinity? It is not going to taper off to a number. So as soon as I know I have a slanted asymptote, I know the limit at positive or negative infinity does not exist, okay? So I can tell you that limit does not exist. But again, I can justify that. So let's do that part. So the highest power of x, x to the 4th, okay, 2, x cubed over x to the 4th, x squared over x to the 4th, 1 over x to the 4th. So all 3 of these terms go to 0. So what am I left with? 2 over 0, which is undefined. So indeed, that limit does not exist. Okay, let's see. Limit at infinity. Okay, so I mean, I have a couple of ideas. So my first thought is, well, each of these limits exists. So couldn't I say then the limit would be the limit of each term? Because both limits exist. So that would be 0 minus 2. Okay, or I could try an LCD. So let's see, I guess I'd multiply by t minus 1 and then by t. Okay, so what is that? Negative 2 t squared plus t minus 1. Okay, then I can see, look at the leading terms. I can see that result's going to be negative 2, but again, I can justify that dividing by t squared. All of these go to 0. So either way, I can see the result is negative 2. Okay, let's see. First thing to notice with this is I'm looking for the limit at a number. So if I'm looking for the limit at a number, I know what I want to do is I want to simplify. So I'm not looking at the horizontal asymptote then. That's only if I'm looking for a limit at infinity, okay? So what I do, I could try plugging 2 in, but I get indeterminate. So that means I want to simplify the expression. So I have a fancy difference of squares at the top. Okay, and then looks like I have another difference of squares. Here. Notice that sums of squares are prime. That means that one does not factor. Okay, but the difference of squares will factor. So that's x plus 2, x minus 2, and then my sum of squares stays as it is. Okay, and then I can cancel. Okay, and then I should be able to actually plug the value in, because that expression is now defined at x equals 2. So my result looks like 32. Okay, limit as theta goes to pi over 2 of cosine of theta. Oh, well actually isn't this one really easy? Because, I mean, if you wanted to, you could graph cosine. Looks like this, doesn't it? So isn't this function continuous at pi over 2? In other words, can't I just plug pi over 2 in? Isn't cosine of pi over 2 just 0? So that one's really easy.